Chapter 20, our last one, was called Understanding Energy, and we really were focusing on breaking bonds, forming bonds, and the implications that had on a chemical reaction. We introduced the idea that if we were going to break bonds in a compound, that's an endothermic process because the bonds have to absorb energy to break, to pull those atoms apart from one another. And to form bonds, when the atoms come together, like after you break the bonds of the reactants, and then once those atoms come together to form product, they're going to release energy. They're becoming more stable, they're going into a lower potential energy state, so they give some of that energy back. And we use the mnemonic BARF to help us remember, maybe, that breaking bonds absorbs energy, and that energy is released when bonds form. The most important thing to understand is that all chemical reactions involve breaking bonds and making bonds. Therefore, every single chemical reaction absorbs energy, and every single chemical reaction releases energy. It's not just the endothermic ones that absorb and the exothermic ones that release. Every reaction absorbs, every reaction releases. We call something endo or exo based on what is more. Is there more energy absorbed than released? That would be endo. Or is there more energy released than absorbed? That would be exo. We looked at the average bond energy table, or enthalpy is another word, but energy is what we used. So the average bond energy table is giving us a bunch of different bonds, most of them, pretty much all of them, between nonmetals. So they're all covalent bonds sharing electrons. And the energy value that's given is how much energy would be required per mole of bonds to break them, or how much energy we would get back would be released per mole when that specific bond forms, and they're different for every single bond. The way we use the table is to look at a reaction after it's balanced and calculate the energy involved to break all of the reactant bonds and the energy we get back when the product bonds are formed. So here's methane. It was one that we did in class. And again, it's for the balanced equation. That's really important. You have to balance it first to see what the mole ratio is because the bond energies are per mole. 1 mole of methane reacts with 2 moles of oxygen to give you 1 mole of carbon dioxide and 2 moles of water. So here you're breaking 4 moles of CH bonds. So you're going to do 4 times the value of the bond energy for carbon and hydrogen single bond. And then you're breaking 2 oxygen-oxygen double bonds. You're going to do 2 times that value. And that total is 2,648, according to this. The values, if you're using a different table while you're following along, the values are going to vary slightly because the values are different depending on what source you get the table from. But this would be 2,648 kilojoules of energy absorbed to break all of the bonds in the reactants for that balanced equation. Now, when those atoms are separate like that, that's what happens after the bonds break. They're going to rearrange and form new bonds. You're forming 2 moles of carbon-oxygen double bonds. You're going to do 2 times the bond energy for that. And then 4 moles for oxygen-hydrogen single bonds. 4 times the bond energy for oxygen-hydrogen single bond. They're using negatives here because negative indicates that energy is released. It's not that important. The big takeaway is that you're getting out 3,466 kilojoules of energy from making all of those bonds. So again, like any reaction, this reaction had energy in to break bonds and energy out when bonds form. What we want to know, though, is the reaction endo or exothermic? Was there more energy going in or more energy coming out? In this case, there was more energy coming out. And the net energy is how much more energy came out of that reaction, and that is 818 kilojoules as a net loss of energy, classifying this as an exothermic reaction. The delta H, or the net energy here, is 818 kilojoules. There's a couple of examples I gave you on the back here. The first one is showing the production of hydrogen bromide. So the balanced equation is H2 plus Br2 yields 2 HBr. The bond energies were provided here, so it's 1 mole of an HH bond that you're going to break. You're breaking 1 mole of a Br-Br bond, that's going to be 193 kilojoules. And then you are forming 2 moles of an HBr single bond. So you're going to take the bond energy for HBr and multiply it by 2. And then what we're going to do is, if we want to look at the total energy that's required to break the bonds for this balanced equation, it would be 432 plus 193 would be 625 kilojoules, and then the total energy that we get back is 363 times 2 is 726 kilojoules. There's more energy out than in. How much more energy? Subtract the two values, and we get that the delta H, or the net energy, is 101 kilojoules released. Right? There was a net release of energy for that reaction. For example 2, it's probably best to draw out the Lewis dot structures for these so you can see what bonds have to break, how many bonds have to break, so that your math becomes a little bit easier. It's 1 mole of methanol, 3 moles of O2 is what you're breaking. You're forming 2 moles of carbon dioxide. And you're forming 3 moles of water. 1, 2, and 3. So in terms of the bonds that we have to break 1, 2, 3 oxygen-oxygen double bonds, and the table that I'm looking at says each one is 498, so I'm going to do 3 times 498 to break those bonds. We have to break 1 carbon-carbon bond, and the value that I'm looking at says 347 for that bond. We also have to break 1, 2, 3, 4, 5 carbon-hydrogen bonds, which I have a value of 413. We have to break 1 carbon-oxygen bond, which is 358. And then we have to break 1 oxygen-hydrogen bond. And my value for that says 467. I'm using the big table that I gave you guys in class. So in terms of total energy absorbed to break these bonds, I'm going to just add all those things, all those numbers up in the calculator. 347, 58, 67, plus 498 times 3. I get, I'm going to ignore this water. I'm just going to use this reaction here. I get 4,731 kilojoules absorbed. I'm going to just plug that in my calculator again because I did it pretty quickly. It's a good idea just to double check when you have so many numbers in here. 347 plus 467 plus 358. 4731. Now in terms of the bonds that form, we are forming 4 moles of carbon-oxygen double bonds in carbon dioxide, so it's 799 times 4. And I'm going to add that to, we're making 1, 2, 3, 4, 5, 6 moles worth of an oxygen-hydrogen bond, which is 467. So 799 times 4 plus 6 times 467 is 5,998 kilojoules. So this reaction also has more energy out than in. How much more? We can subtract the two and get that the net energy, or delta H, of the reaction is 1,267 kilojoules released as a net energy value. If you do the water example, we did that one in class and we had it in the notes section, so I think this one was a better one to practice with. After that, we looked at, now that you have all these numbers, how can we pictorially represent what that looks like in terms of an energy exchange diagram, or what we called also a potential energy diagram. And that's showing the energy in, the energy out, and the net energy. So here, the energy in, for example, the formation of water. This isn't for the methanol reaction we just did, or the ethanol reaction. This is for the formation of water. You're breaking the bonds of the reactants. You're getting energy out. Because you had more energy out than in, that's why it's an exothermic reaction, and it takes the shape it does, and then the net heat released is the difference between the products and the reactants. For this reaction here, for the ethanol one we just did, if we wanted to sketch what that would look like, we can do it in a couple of ways. We can do a quick sketch like this just to show it's exothermic, and your products are ending below where your reactants are, or what we can do is actually say, okay, my reactants are starting here. They absorbed 4,731 kilojoules of energy, but we got back 5,998 kilojoules of energy, and the difference between the two is your delta H, or the net energy, which is 1,267 kilojoules of energy. So you can show the diagram like that. Either of those two ways is fine. You should be familiar with recognizing an exothermic versus an endothermic energy diagram, products and reactants, their placement. Remember, it's plotting potential energy, so which one has the higher potential energy, which one has the lower, how potential energy changes and kinetic energy changes in response. So the potential energy here is decreasing, which means kinetic's going to increase, and then potential energy is increasing here, so kinetic's going to decrease. The activation energy is the distance from the reactants to the top. It's representing how much energy has to go in to start the reaction, right? It's the minimum amount of energy required to start. And then the energy absorbed or released, the net energy, or delta H, is represented by this arrow here. Remember, they're reverse. If you're looking at the reverse reaction, they're sort of inverses, a flipped image of each other. The last thing that we looked at was rates of reaction and how to affect rate. So we looked at something called the collision theory, which says that if reactants are going to turn into product, they need to collide. Their collisions have to be effective. An effective collision is one where the reactants collide with the proper energy and the right orientation in three-dimensional space. If they don't have the right energy and they have the wrong orientation, then they can collide, but there's no product that's going to be made. The more effective collisions we can make, the better chance of making a product, and then that's why the rate of the reaction would increase. We looked at a couple of different factors that we can change to affect the rate of the reaction. That was concentration, temperature, surface area, pressure for gases. Pressure is a way to change the concentration for a gas, and then catalyst. You should be familiar. I'm not going to go over all of them in detail here. The pictures do a nice job, and you have it in your Chapter 20 note packet, but you should be familiar with the relationship between each of the factors and how they affect rate, and be able to explain in words why or how that factor affects rate. The one I will go over just to show on these diagrams is how a catalyst works. We said that a catalyst, we know that it increases the rate of reaction. It does that by lowering the activation energy. So if we had to draw what a catalyst would look like, or how it would change a potential energy diagram or an energy exchange diagram, it would lower that middle section. It doesn't change where the reactants are starting or the products, right? It's not changing the energy they have. It's just changing how much energy the reactants would have to absorb. So here's the activation energy now for the catalyst in the red line. You can see it's significantly lower, and that's the reason why catalysts would increase the rate of the reaction. By decreasing the activation energy, the reactants don't have to absorb as much energy to start their reaction. So again, be familiar with the different factors, the relationships with the rate of the reaction, and then be able to briefly explain how they affect the rate in the way they do.